Bismillahirrahmanirrahim. This lecture is basically the continuation of our previous lecture, which was on traction vector. Now we want to discuss the stress tensor. So to discuss the stress tensor, we will find the expression for the traction vector acting on a surface of arbitrary unit normal. Means that its normal will be in any arbitrary direction. So let us consider an orthonormal reference frame. Let delta Fi be the ith component of the force delta F exerted on the surface element delta Sk. On the surface element delta Sk. This is the surface element which is perpendicular to the k axis. Means that if it is delta S1, then it would be perpendicular on x1 axis. That is, it will lie in x2 and x3 plane. This frame is shown here. This is x1, this is x2, this is x3, this is surface element delta S2 for the sake of example. This is delta F2, this is delta F3, and this is delta F1 in the x1 direction, in the x2 direction, and F3 direction. And normal of this element is in x1 direction. So we can write the stress Tik as the limit with delta Sk approaches to 0 of this ratio, like we have discussed this in our previous lecture. Tik will be equal to delta Fi over delta Sk with limit delta Sk approaches to 0. So this will be dFi dSk. No, this Tik is the ith component of force exerted on a unit surface perpendicular to the k axis. Ith component of the force exerted on the unit surface perpendicular to the k axis. And from the figure, as I have told, that this delta S2 is an element with and this is orthogonal to the x2 axis. That it is lying in x1 x3. Earlier you said that x1 is perpendicular to this, not x2 is perpendicular to this surface element with area delta S2. So x2 is the normal of this element and is lying in x1 x3. So how many components and which are the components will be there? If we have delta S2, so we will have, if you will put 2 instead of k, it will be ds2 and it will be di2. So these can be t12, t22 and t32. Now, as I have said that we will have to calculate the expression for the traction vector, and with the help of that we will see that which are the components of stress tensor, and we will show that how the components will denote the second order tensor, which is called stress tensor. That we will show that we have these 9 components tik, and these are the components of a second order tensor. That we can have 9 components from this equation number 1, t11, t12, t13, like this up to t33. So we will show that how these are the components of a second order tensor. But before that, we must have expression for traction. Now, to get that, we will start from here. That to study the forces within the continuum, we wish to describe them with respect to a plane of arbitrary orientation. So for this, let us consider an element of the continuum in the form of a tetrahedron. Tetrahedron is a geometrical shape having 4 faces, triangular 4 faces. Suppose that this tetrahedron is spanned by these 4 points O, A, B and C, and you can see that this is the origin, and A is on the x-axis, y-axis, z-axis. This is shown here. A x1 axis, B on x2, C and x3, and if you will join these two, B, C, A, B and AC, you can see that it will have 4 faces. 3 are orthogonal faces. This tetrahedron is formed by the surface element. 3 faces are the orthogonal faces. Orthogonal means they are on the coordinate planes and they are orthogonal with each other. And these are AOB, OAC and OBC. These are the 3 orthogonal faces on coordinate planes, and one ABC is the oblique face. Basically, this tetrahedron is formed by the surface element ds, and this oblique face has we have 3 orthogonal faces. We have 3 orthogonal faces and these should be like this: OBC, OAC and OAB, with areas DS1, DS2 and DS3 respectively. So please make correction here. I will send the corrected file of this article, corrected PDF of this page. So it should be OBC, OAC and OAB, with areas DS1, DS2 and DS3 respectively, and area of this oblique face ABC is DS. Normal of this ABC is in any arbitrary L direction, and normal or other 3 orthogonal faces are minus E1, minus E2 and minus E3, means minus x1, minus x2 if you have x2, that if you imagine the tetrahedron, then you will see that their normal will be in opposite direction. Suppose that your projection is in x2 and x3 plane, then its normal will be in minus x1 direction, outward minus minus x1 direction. After imagination you can understand this thing, after imagination of this tetrahedron. Now areas of projections and volume of tetrahedron with area of oblique face as follows. And these are the relations between the areas of tetrahedron, between the area of the oblique face with the areas of orthogonal faces, and between the area of oblique face and with the volume of tetrahedron. Now this is dsi is equal to li ds, that ds1 will be equal to l1 ds, ds2 will be equal to l2 ds, and these l1 l2 l3, what are these? These are the components of this unit normal L. And here we are taking ABC is the base of tetrahedron, volume oblique face, dV is equal to h by 3 di. H is the height of tetrahedron. Now force acting on the element ds, as I have said here, this is TL. T of L ds, and force acting on ds1, it will be minus ti1 ds1, because normal is in minus i1 direction, minus x1 direction. This is minus x1 direction. It will be in the opposite direction of x1. This is lying in x2 x3 plane, this face whose normal is minus x1, lying in this plane x2 x3, then normal is in minus x1 direction. So that is why here we have minus, like minus di2 ds2 minus. If we have plus x1 plus i1 direction, normal is plus i1, so it would be ti1 ds1, no minus. These are all the surface forces. Now we will go for the body force, because the tetrahedron has also the volume, which is dV with mass rho. Now this F is denoting the density of that body force acting on the tetrahedron with volume dV and mass density rho. So state of equilibrium says that sum of all the forces acting on the tetrahedron must be equal to 0. So surface forces plus volume, the force, body force, sum will be equal to 0. So we can write this equation, and here we have taken basically any ith component, ith ti til ds minus ti1 ds1 minus ti2 ds2 minus ti3 plus rho dv fi is equal to 0. So we know we can write this thing as by putting ds1 equals to l1 ds, l2 ds, l3 ds, and we are taking ds common from these four terms, and we are using h by 3 volume, dv is h by 3 ds. This can be written in this form. We have cancelled out this ds from both sides. No, to describe the state of stress at a point within a continuum. In the start, we have taken an element of the continuum in the form of a tetrahedron. No, we want to describe the state of stress at a point within the continuum. So how can we obtain that point? By simply taking the limit h approaches to 0, that if the length of tetrahedron approaches to 0, then we have a point within the continuum. So when h is approaches to 0, then it means that all the areas of all the forces simultaneously approach 0. This is obvious. In other words, that we are saying that the finite size tetrahedron reduces to an infinitesimal tetrahedron, very, very small tetrahedron at a point 0, 0, 0. So in this case, when h is approaches 0, this will go to 0 and we will be left with this only. So this is the expression for the traction vectors, for the traction vector acting on a plane whose normal is any arbitrary direction with area ds t1, t2, t3, and the components tij, these are the components of a second order tensor, and we see that this second order tensor and this tensor is stress tensor. This is these ti are the components of vector t, traction vector, and these lj, these are also the components of a unit normal on that surface. So this must be a tensor of second order, and we are saying that this tensor is a stress tensor. We will show that how these are the components of a second order tensor. This is we have to show by using our fundamental definitions about the components of tensor, in which we have studied the transformation laws, where we say that a second order tensor must satisfy, the components of second order tensor must satisfy this type of transformation law, a particular transformation law, like third order, fourth order, fifth order. Now we will show that these components satisfy a transformation law corresponds to a second order tensor components. As this is components of vector, so we will use the definition of the transformation law for the components of vector. I have written this, so you can write Tij Lj equals to this dash Im m, you can write T dash L dash. I have replaced J with N. You can do this. J is dummy, you can write whatever the letter you want to use, except this M. You cannot use this M again, because M is already dummy here in this term. Now we know that Ln, these are the components of vectors, so we can write this thing Ln dash equals to Qjn Lj. So it is Jn, not Nj, this is Jn. Using in one, we will have this do a little rearrangements. QIM, QJ, and T dash M and LJ. As LJ are the components of an arbitrary vector. So we can write Tij is equal to this. So this will be equal to this. Now this is telling that Tij are the components of a second order tensor, and we see that this tensor is a stress tensor. Now it has 9 components, obviously. T11, T12, T13, T22, T23, T33, T1, T2, T3. Diagonal components are called the normal components, and other components of diagonal components are the shear components. Next we will show that as strain tensor is a symmetric tensor, this stress tensor is also a symmetric tensor. So before going to that, we will study the equilibrium conditions. Thank you so much.